Hello, hello, hello. Welcome to my latest live stream. So this is live stream number 30 of my series of live streams talking about the Boeing Starliner propulsion anomalies, essentially through the lens of STAMP, STPA and CAST. So if you're interested in STAMP, STPA or CAST, then please, stick around. Type in the chat, let me know you can hear me, let me know where you're watching from. And of course, if you've got any questions, if you've got any experience you'd like to share, please, stick that in the chat and we can go from there. But just be aware, there is about a minute delay between what I say and what comes out of your computer. And then, of course, if you write a response, that's going to take a little while to get back through to me. So just be wary of the delay. So if you don't know who I am, my name's Simon Whiteley. I'm a system safety engineer and accident analyst from the UK. I specialise in STAMP, everything to do with STAMP, STPA and CAST. And if you need any help or support with that, then you're welcome to get in touch. Pardon me. So my website, if you want to get in touch, my website is located at whiteley-safety.co.uk. And if you need any help and support, you're welcome to click this big green button, I need help now. Send me a message and we can set up a call. You might have have a question, or you might be a bit confused about something. A 5-minute conversation with me will help sort that out. And of course, if you've got something really serious going on and you need some really serious expert help, please send me a message. We can set up a call and see how I can possibly help. Now, this whole sort of series of live streams is essentially been me working through the official investigation report with a view to put on a free event, a free workshop, where we'll talk about this topic live together on Zoom, not in a broadcast style like this live stream is. But if you visit the link in the description or visit my website on the homepage, you'll see a button for this free workshop. Just stick your name and email address in there, join the waiting list, and then when I've finished the live stream, hopefully today will be the last one, I will be putting together a slide pack, some control structure models, ready to get together live. If you join the waitlist, I'll send you a message, send you the details, and we can get together and talk about this live on Zoom. So fantastic. Let's just check that the audio is working. It seems to be. That's good. Nobody's screaming at me saying that there are some issues, so that's positive. But as I say, if you do have any comments, just please stick them in the chat and I'll get to them as we progress. So with regards to the official investigation report, we've essentially got through everything now, and we're just finally working through Appendix G, which is the STAR and SDRT report. So it's like two investigation teams doing their own sort of focused investigation, and then that report has been combined and is an appendix to this main report from the NASA PIT team. So we're just going to continue through Appendix G. It is about 104 pages. We've already got through quite a lot of it so far, so we're going to continue tonight. This is going to be a long live stream. I'm going to try and go through for about 3 hours. We'll see where we get to. And then if we can't finish it in that time, then I'm going to have to schedule some more sessions to get that sorted out. I've got a few projects on the go, so I need to try and close this one down. It's been a bit of a long journey, this one. Okay, so this is just an overview of the Appendix G. So we've already got through this first part, and we've got the helium system issues, which we're going to go through now, the thermal issues, the thruster issues, the SDRT report, the STAR Senior Review Panel comments, and then if there's any relevant appendices that we want to go through. So we're going to continue today talking about the helium system issues. So here we are, helium system issues, everybody. So let's make it big enough on the screen so you can see it. There we go, helium system issues, failure tolerance issue. After the first crew flight test launch attempt, it was realized by the NASA and Boeing teams that the Starliner service module propulsion system was not too failure tolerant for deorbit. So this is before the thing took off. Pardon me. Boeing and NASA did not identify the issue during the phased safety review process when the applicable hazard report cause and control strategy was developed. Okay, so there's sort of two issues there to think about. There is the work done after the first launch attempt, but then also before that is the phased safety review process. So why was it not discovered during that point in time? That's what the investigation should include in its scope. So there we go, let's have a look at this. So figure 97, focused crew flight test, service module propulsion anomalies timeline with correspondence. So this is from 2010 all the way through till 2024 when the crew flight test launch took place. So let's start in the past. So we've got the space agreements awarded. So the first one, the second one, the service module propulsion PDR. So that was, quite early. Then we've got the third SAA awarded. We've got the CPC contract awarded. And then, of course, the preliminary design review, the phase 1 group 3 review, not sure what that is, the critical design review, the contract award, CCT cap, then the contract baseline review, I think it is, then the Delta contract design review. I'm not sure that is the CDR. There's something, I can't remember what that is from last time. Then there is a phase 2 safety review and a phase 2 safety review. So that's causes HR 02.08 and 1601. I think they're hazard risks. I can't remember. Cause 4, causes 8 and 9. And then we've got FT, presumably that's fault tree issue reported to Boeing. No, fault tolerance issue reported to Boeing from MO. Not sure who MO is. FT issue resent to Boeing from MO. So that's in the 2016-2017 time period. Then we've got HRs 2.08 and 1601 phase 3 approved for orbital flight test only. So OFT 1. Then we've got the fault tolerant issue resent to Boeing by MO, noting something really needs to be done. So this is, in terms of time periods, that's, an issue's been outstanding for a long time. So what is it about all of the safety review boards and various meetings that are taking place and trackers and action trackers and all that kind of administrative effort? OFT2, first attempt, valve failures. So there were some valve failures on the second orbital flight test in 2021. Okay, and then we've got OFT2, and then we've got crew flight test, first attempt, helium leak, lack of 2 fault tolerance for EDL PCB accepted, crew flight test launch. So if it's been approved for OFT only, how have we managed to find ourselves in a crew flight test? It's just, there's something going on with the way safety is managed, the safety management system, how these stakeholders interact, and especially how actions are tracked and issues are tracked to closure. Because the safety constraint is, if it's been approved for OFT, there's obviously some actions that need to take place to get this from OFT standard to crew flight test standard. So what is that work? What is that activity? Which stakeholder, which controller is responsible for dealing with that, for doing that work? So background then, the Boeing Service Module Propulsion's System PDR 16. So obviously these references are, you can't see down below, obviously these footnotes are redacted for whatever reason, was held on January the 9th to the 10th, 2012 under the CC Dev 2 contract. At that time, the high helium pressurant system had 3 helium manifolds per doghouse. By critical design review on the 19th to the 21st of November 2023, so that was essentially a year and a half later or so, the system had evolved to 2 helium manifolds per doghouse. So it went from 3, let me get my pen. Here we go. It went from 3 manifolds down to 2 manifolds. So the design has changed quite a lot, and I'd argue if there's a fault tree analysis and a failure modes and effects analysis that is done in parallel to this work, then that will be updated, or would have been updated, should I say. The Phase 2 safety review for the CCTS 02.08, it'd be nice to know specifically what they are, began in February 15 and finished late in 2019. So there's essentially 4 years, well, let's say roughly 4 years review going on in there. I can't spell. There we go. Approximately 4 years review. The review did not identify the failure tolerance issues or flag the helium seal material choice as a hazard cause for leakage of the pressurant. Okay, so there's 2 sort of broad questions there. The first is about how the design work was done, how the safety assessments were done. Then there is a question about how the PDR and CDRs were conducted and any open actions or issues. And then the third is the review itself. What was the review focused on? Why did it miss these elements? Or did it not miss the elements, but they just weren't tracked and dealt with till closure? What's going on there? And as I say, it doesn't really, the document hasn't yet said what do we mean by CCTS 0208 or 16.01. Are these the hazards hazard identifiers or the failure mode identifiers? What are they? It doesn't make sense. And I'm sure, if you're involved in this stuff all day, every day, it'll be really obvious what it is. I mean, if you want to stick it in the chat, let me know. That'd be helpful. That'd be fantastic. Okay, so CTS 08. So this one, let's give it a particular label, shall we? Let's use that color for a change. So CCTS 0208 Rev 020819. Again, the footnote is blankety blanked. That's helpful, thank you. So this has cause for so we've got cause for and control 7 addresses failure tolerance due to leakage of pressurant. but it focuses on CCTS VR, whatever that is, 002, SM propulsion abort pressurization leg fault tolerance. That variance addressed the lack of failure tolerance of the blankety blank, the doghouse blankety blank that were identified as a failure tolerance issue during crew flight test are in a different downstream location. The HR's focus, I think HR means hazard report. That's what I'm guessing. On the CCTS-VR-029. Yeah, this is quite tough to read and get my head around. May have contributed to missing the lack of two fault tolerance in the downstream doghouse. Okay, so this sort of highlights the question about what was the focus of the safety analysis. You know, if it's focused on this topic, is that at the sacrifice of focusing on other things, or is it that the methods that they're using have led them down that path? Because again, it's not really clear here. When we're talking about the hazard report, what is the content of that? What does it focus on? What are the hazards? What are the particular failure modes that they're interested in? What analysis methods have they used? I know it mentions fault trees and FMEAs a little bit earlier on, but this is a bit superficial. It implies that the reader knows a lot, and of course it's a public report, and I'm relatively a layperson, relatively speaking, in relation to this. So it's not really telling us too much. Well, I can appreciate we don't want them to divulge any sensitive technical, or other aspects, but it could do a bit more detailed, I think. And then we've got CCTS 1601. So that's slightly different to the one above. So let's just mark that off. And this is 2017. So it mentions cause 1. There we go. Let's have a look. Cause 1 discusses helium failure tolerance just after control 10. It acknowledges that delivery of helium to the individual thrusters is 0 fault tolerant and points to causes 8 for attitude control and 9 for translation as the location in the report that covers how the system level redundancy achieves functional failure tolerance. So it says there it's 0 fault tolerant, points to causes 8, and number 9 has the location in the report that covers how the system level redundancy achieves functional failure tolerance. CCTS 1601, cause 9, control 1, cause 9, control 1. Let's just make sure it's big enough on your screen. So that one is this one here. Control 1 states that the system is too fault tolerant to the loss of translational maneuvering capability, including any combination of blankety blankety blank. It is not clear how Boeing or the STRB assess the failure tolerance of the pressurant system with combinations of manifold failures. Okay, let's just jump back to here. So there we go, there's the organization chart that explains how some of this works. And there we go, let's hope it's, yeah, so this is the Crew Commercial Program board structure. So there's various review boards and panels and working groups and all that kind of stuff. But these are the boards. And so from a, there we go. So this PCB is the program control board. The TRB is the technical review board, and the STRB is the Commercial Crew Safety Technical Review Board. So that's what this is here. That's what that is there. Let me just highlight that for you. So Boeing have done an assessment, and the STRB have done an assessment of the fault tolerance of the pressurant system with combination of manifold failures, but it's not clear how they've done that. So there'll be some kind of hazard analysis report, a hazard report of some description, maybe a fault tree analysis or some other analysis report associated with it that will look at these specific topics. But it says there it's not clear how they've done that. So why is that? Why is it not clear? A rigorous blankety blank assessment of the pressurant system should have identified the fault tolerance issue with a common reaction control system and orbital maneuvering and attitude control helium manifold before approving a phase 2 hazard report. Okay, so I'm not sure what a phase 2 hazard report is in this context. I think it might be that it's there we go, let's just mark that up. Phase 2 hazard report. So it's likely that it implies, or my impression is that a phase 2 hazard report is a report that is done, not to generate requirements for the design, but to identify. Sorry, what am I talking about? It's not intended to generate functional requirements. It's designed to assess the design and identify or generate any other more specific requirements. Not that it's trying to confirm that it's acceptable or not. That's my impression. I'm probably talking a load of nonsense. So if you know, please stick it in the comments. Give me some abuse. Give me some advice. That'd be appreciated. Oh, there we go. It says there the phase. Can't speak. The phase 3. Oh, sorry. Phase 3 safety review. Hang on a second. I think it's probably referring to these safety reviews. A phase 2 report is an input to this review, and a phase 3 is probably for later on. I don't know. It'd be nice if there was a reference to a safety management plan of some description that described all of this that we could look at. Even if it was just a Gantt chart to show the activities and deliverables and dependencies. Okay, so the phase 3 safety review of CCTS 1601. So that's this one up here. There we go. I'm getting slightly better using this pencil after 30 live streams. Let's zoom in a bit so you can see. There we go. So the phase 3 safety review of CCTS 1601, whatever that is, should have, everybody, should have. It wasn't, so why wasn't it? Let's not blame them too much. Should have been another opportunity to identify the fault tolerance issue. The expectation is the commercial providers are the experts in their systems and will bring forward a complete picture of their systems and any requirements variances, including shortfalls in failure tolerance. Pardon me, CCTS 1601 Cause 9 Control 1 verifications So cause 9, control 1, verifications. So that's this one up here, down to here. Verification 1A should have identified the failure tolerance issue. That verification did not change in OFT, OFT2 or CFT, applicable report causes. The Boeing submitted that verification closure and NASA approved the verification, even though the documents referenced in the verification were not sufficient to verify the hazard control. So if I'm interpreting that, so Boeing submitted that verification closure and NASA approval, the verification, even though the documents referenced in the verification were not sufficient to verify the hazard control. Okay, so I can appreciate what they're saying there, but my understanding based on everything that's gone before up until this point is that it is their responsibility to make sure everything is tickety-boo. NASA approving it, it's not that they are approving and agreeing with the safety assessment. That's not how it's written earlier on in the document. So it seems there's a bit, when this statement was collected, it seems there's a bit of a misunderstanding about who's responsible and who should be liable. That is the party that's supposed to be responsible for the safe design and the safe design, and that the design is adequate and meets requirements. Yeah, okay. I mean, this is the kind of thing that happens though. If you change the assurance framework, which I think is the term they used in the previous sessions, it muddies the water. It muddles things up a little bit. Boeing is the ultimate, design authority of the spacecraft and should be looking after and making sure their suppliers are doing what they need to do. But it's not up to NASA to approve the design and accept the risks associated with that. Or that's not how it's been. That's not how I've understood it. And so for them to say it in that way implies that NASA are also to blame. It's their part. They need to walk the plank as well, and I'm not sure that's really what the intent was. Verification 1A refers to. Let's just. Oh no, that's not what we meant to do. So verification 1A refers to attachment 2. And the guidance, navigation and control CDR as verification. Attachment 2 references table 2 and 3 for translational control authority. The information in attachment 2 is not sufficient to demonstrate that the system is too fault tolerant. Right. Okay, I mean, I can't say I'm surprised that this has got through. I've seen similar sort of things flowing through various programs over my years, so I'm not surprised. Obviously, it's disappointing, but there's something going on here from an organisational perspective, roles and responsibilities, the processes they use to do the work itself, the way the work is organised, the way it's scheduled, the way actions are tracked or forward actions need to be tracked to closure, and the way that they are kept on the agenda of the various technical review boards, or the safety review boards, should I say. And then, of course, how all this fits together. So there's potentially a lot here that needs to be looked into. And I'd argue that this is a systematic issue. This is not just this particular, part of the design. I would imagine that there's issues like this in potentially many other different areas. It's just that obviously this is the subject of the propulsion anomalies. So I'd suggest that, we go hunting for other instances of this kind of difficulty, in other subsystems as well. This won't be isolated. I would not expect it to be isolated. Verification 1A also refers to the guidance, navigation, and control CDR. This section does not address failure tolerance other than to assess stability requirements. The verification artifacts pointed to by verification 1A do not verify the hazard control. It is unclear how Boeing approved the verification or how the SDRB was able to verify their work. Yeah, so that needs to be worked out and figured out, because it'll apply to a lot of different subsystems, not just this one. In November 2016, an FOD mission operations employee supporting the Starliner team identified the failure tolerance problem. Fantastic. And that was 2016, and sent an email to Boeing's engineering leadership discussing the issue and potential resolutions. That employee followed up again on that email. Oh, here we go. In May 2017, resending that issue to the same distribution, the employee sent a third follow-up email in April 2021, noting that this has been languishing for some time now, and we really need to do something with it. Oh, I shouldn't be laughing. This is crazy. Oh, actually, I'm not surprised. This is the kind of stuff that goes on in big programs. I'm not surprised. Just incredibly disappointed. But whoever this person is, they're a star. Keep up the good work. I mean, it's good that there's continuity over that period of time. What's that? 5 years. It's good that they've got that continuity, because it could be that the exact same thing could have happened, but they only sent the email once. But again, there's a question there over how do you manage a program of this complexity with these kind of issues? Because is an email actually an appropriate way to notify the organization of issues and then get those issues resolved? Emails are shockingly bad for that, especially in healthcare. Some of the healthcare examples I was looking at over the last 12 months working with the UK's Healthcare Services Safety Investigation Branch. One of the issues with patient safety is how safety critical information and decision making and justification is captured and stick it in emails instead of a formal logged database that people have access to is a surefire way to miss stuff that's really serious. I mean, this is similar. And again, I'm not criticizing individuals. If that's all they've got to work with, then they're doing the best that they can. But it is incredibly manual and should be better managed than this. I wonder if the STRB, Commercial Crew Safety Technical Review Board, do they have an issues list or a shit list, so to speak, that lists all of these issues? Or is there some kind of central tracking system for these things? Or is it left up to individual workers doing the work to track it themselves? And if they leave the company or if they move on or something bad happens, is that part of the control loop completely broken now and that issue is just overlooked and ignored? How is this dealt with? Again, this is not a specific issue for these individuals in this part of the organization. This will be a program-wide management issue that needs to be addressed. So how are they doing that? How are they managing that task of keeping track? So forward actions, issue tracking. I can't write today. There we go. Tracking. And you could argue that this is part of the safety information system. So if I just quickly zoom out to the conversation we were having the other, there it is, that one there, that's what I wanted to go to. So if we're talking about structure analysis, this is a topic related to safety information system. We've got issues with safety documents, V&V. How are those issues tracked to completion? both from an administrative perspective, but also from a safety management process perspective. Pardon me. Yeah, I'm just... And again, let's have a look. So this was an FOD mission operations employee supporting the Starliner team. So when we say Starliner team, is that the Boeing team, or is that the NASA team, or is that the CCP team? And when we say supporting, was it that they would just ask, hey, can you just have a quick look at this? Or were they formally part of the program and tasked formally with whatever, like if they're doing a review of the documentation and they spot this, was their issue put into the formal issue tracking system or in the review comments tracking system, presuming they've got one? How was that closed down? Because you're not supposed to be able to close a review down until all of those issues have been dealt with. And I say you're not supposed to be able to. Being very cynical, having been in similar roles myself in the past. Okay, and I suppose also that raises questions about how do you hand over safety-related work and open actions and issues between employees and teams? Because people move on, move around, whatever it is. How do you make sure that those, that issues list is actually handed over properly? Especially, I mean, I don't know if you've got a 2-week notice period or whatever it is in the US and people have to leave or they're made redundant. How do we make sure that we're handing over information and actions properly? Anyway, let's keep going. Right, Boeing engineers and engineering managers were notified. They were notified that there was a failure tolerance issue prior to the OFT flight tests. So they're meant to, so if we get our little jigsaw piece, here we go, everybody. So they've received some feedback from some. In fact, actually, let me just zoom out a second. Let me get this other one. Where's the other one? It's around here somewhere. Where is it? Where is it? Where is it? There it is. Right. Let's just take this one and paste it over here. Right. Let's get that big enough on the screen. So let's imagine for a minute then. And this is not a representative control structure. This is just one that I use in my training to get people's juices flowing, creative juices. So if you imagine that this is the engineering team in Boeing and their control process is making sure that their design is a safe design and doesn't have any issues with fault tolerance or, doesn't meet requirements, whatever it is. And then you've got this other controller, other member of staff, other team member, doing some reviews or whatever it is. They've got a belief there's a problem with the fault tolerance. Their decision is they need to notify whoever it is that's dealing with this, the engineering leadership, task managers, whatever it is. So they've done that 3 times. And so it appears that this controller hasn't done anything about it. So, why is that? Why would it make sense? What decisions were they making? What were their beliefs? Were they receiving direction from above to discount it or disregard it? We don't know. That's what the investigation should go and find out. And I hope you can see, just by using this simple, little jigsaw puzzle with a few jigsaw pieces stuck together, you can start to ask really powerful questions and really get to the crux of what's going on here. And that enables you to make better recommendations. Because one of the recommendations I was discussing, well, how, these inputs that go into, the other party, the other stakeholder, how are they actually tracked? How do we make sure that we're not missing something if someone decides to leave or something happens? How do we make sure they're not lost? Who is the information manager or the communications manager? Is it something that also goes to the Safety Technical Review Board? If not, why not? How is the Safety Technical Review Board involved in this? We don't know. It doesn't say yet. Maybe it'll explain in the next few pages. Let's keep our fingers crossed. Okay, so the issue was not communicated to NASA FOD safety, NASA engineering, or commercial crew program personnel. Oh, that is very interesting. It is unclear whether Boeing engineering communicated this issue to Boeing safety personnel. The STAR team believed this was a missed opportunity to identify the fault tolerance issue earlier in the design phase, perhaps due to competing priorities and limited resources. Well, yeah, perhaps due to, okay. Right, so there's a few other stakeholders there that we might want to document for consideration as candidate controllers in our control structure. So we've got the, where is it? We've got an FOD mission operations employee. FOD mission operations. And then we've got, let's have a look. We've got the Boeing engineering leadership shop. There we go. We've got the STRB, which we already, there we go, that one. Stick that in there. FOD, Boeing Engineering Leadership. And then we've got Boeing Engineers. Then we've got Boeing Safety Personnel. So are they the safety engineers, or are they operations safety people, or who or what are they? It's not clear at this moment. So then we've got NASA FOD Safety, NASA FOD Safety. So a lot of people with safety in their name. Then we've got NASA Safety. Then we've got NASA Engineering. Then we've got Commercial Program. Pardon me, Commercial Crew Program Personnel. Can't spell commercial. There we go. NASA. So let's put those in piles then. So we've got NASA. We've got Boeing. We've got FOD Mission Operations. So I'm assuming that's on this side. Then we've got the Crew Commercial Technical Review Board. We've got the Crew Commercial Crew Program. Right. Okay. So all I've done is put the names, labels of these entities as candidate controllers in my control structure. And straight away the question comes, well, if you've got a FOD mission operations person and they are providing, control actions arguably, or feedback arguably is a question there. Is it a control action? Is it just an interaction, or is it a type of feedback that goes to Boeing engineering leadership? Once that's been passed over, is that their job done? Is that an acceptable, reasonable thing to do? Is that what is required? Is that what they're trained to do? Or is there an implied, you send safety-related actions or issues to a centralized position that logs it in a database, and then all of those other stakeholders have access to that information, and it's on their task list or their issues list. Because it sounds like it was just passed straight across over here, and then for whatever reason, it's not found its way elsewhere or appropriately addressed. So why was that? What's going on there? Let's go and explore the control structure. And I mean, it says here, perhaps due to competing priorities and limited resources. Yeah, absolutely. But instead of saying perhaps, surely the job of the investigation is to go and figure that out. Let's go and figure that out. What, instead of this being a perhaps, what is the recommendation here? Let's go looking. Let's look at the control structure. Let's see what's going on. Because this is, I'm pretty much, I'm willing to bet 10 American pounds that this is a common issue that covers many issues. A common issue, a common systematic fault or issue with the architecture of the organization and the way they interact that will not only affect this issue, but potentially many others. And, of those many others, how many are potentially as serious as this, if not worse? Okay, so findings. Let's zoom in so you can see this okay. Let's not make it too small. Right, findings. CCP did not perform a sufficient Phase 1 safety review. Okay. Why would it make sense for them not to do that? Rigorous channelization of the helium pressure system was not performed as part of the phase safety reviews. When we say channelization, is that a physical architecture, or is that related to the control architecture, or what is that referring to? Again, I'm a bit of a layperson in the detail of this. Focus of channelization that was performed was the hypergolic propellant system, not the helium pressurant system. Okay, so perhaps there is a decision that's been made due to the level of risk perceived involved. So a hypergolic may have been perceived as more dangerous, and so it's got more attention. The helium system, perhaps, I don't know. I think hypergolic propellant is a particular ground hazard when the system has been designed, built, and getting ready for launch. So, of course, they want to pay attention to that. But in terms of helium pressurant system, that's more of a propulsion issue. More focused on being a propulsion issue than it is if it escapes, I would presume. Quantity of helium available to support ascent aborts led many to consider a leakage impact in nominal operations, including service module disposal, as a non-credible failure scenario. Oh, gosh. Everyone loves non-credible failure scenarios. When we say non-credible, are we focusing on... Let me just get on my high horse for a minute. Let's just think. So if we have severity times probability equals the risk, right? So are we saying there that we're not really too worried about leakage, so the severity is not too bad, it's not a big issue? Or are we saying, well, it is quite serious, but we don't think it's very likely, so the risk is low, so we're not going to pay much attention to it? Is that the kind of decision-making control algorithm going on? What about the independent review? How was that organised? Did that have sufficient experienced, suitably qualified and experienced people? Okay, so CCTS 1601, cause 9, verification 1A. So where is it? Cause 9, verification 1A. Okay, so that's over there. The artifacts reference do not verify the hazard control's assertion that the system was too fault tolerant. Just on this topic, I mentioned last time about a useful model to create as part of a safety case or independent safety review. And that is to get a list of all of these safety documents, references, including their dates of publication and their versions. And if you want to get really detailed, you could also include drafts. So how long did the draft version 1 take, before it was accepted for issue? How many review cycles did it go through? How many review comments did it have? What were the classification of those review comments? Were there any serious big questions that were, all of that how could we put it? All of that qualitative information can give you an idea as to how good the reports were, how good the reviews were, and then how painful it was to get them over the finish line, and potentially how much pressure was placed on the various reviewers and authors to get the damn thing out the door. I'm sure you've been in similar situations. And so if you put together a timeline of what these safety documents are, how they're reviewed, when they're reviewed, maybe even link to the review comments if you have access to that information. And then also the stuff that comes out of those documents. So things like the list of hazards, how those list of hazards has evolved over time. What controls and mitigations, for want of a better description, have been applied to those various hazards. Are there any open questions or open actions? And keeping a track of that, an overview of the whole safety case, is very useful. But of course, that requires a lot of effort to set up. And then once it's set up, it's relatively straightforward to maintain. And then it helps to talk with independent reviewers. An independent reviewer can ask a difficult question, and you can literally point through to where that question is addressed. So it can be auditable. And I think in this case, it'd be good to know, what do we mean by 16.01 Clause 9 Verification 1A? What reference does that go to? Is it a specific, version, issue, date of a document, or is it a suite of documents? Is it some emails that don't have, that is backed up with engineering judgment instead of some kind of formal analysis? And I can appreciate I'm coming at this from a safety case independent review perspective, and perhaps they don't use that sort of mindset or perspective in this context. But maybe that's a suggested idea for the future. Have an independent safety case review that actually digs into this stuff in an appropriate level of detail. And I think given all the nonsense that's happened in this particular case, that's probably a good idea. Okay, so Boeing submitted the verification for approval. There we go, that one, is it? CCTS 1601 Clause 9 Verification 1A for approval. Is it approval or is it concurrence? That's what I was saying earlier on about the roles and responsibilities. Surely Boeing should be approving its own stuff because it's supposed to be responsible for it from a technical and safety perspective. And NASA should be looking at it going, yeah, well, it looks all right to us. We don't know any detail of the design, so how are we supposed to assess whether it's good enough and it's approvable? And again, if Boeing have submitted it for approval with incomplete verification evidence, why would it make sense to do that? Because just saying that sounds super bad. Like, hang on a minute, if they've submitted it for approval with incomplete verification evidence, did they know they'd done that? Did they know they've got incomplete verification evidence? Because on one hand, it looks really bad that they've done that. It looks really questionable. But on the other side, it could be, well, they believed they had the right verification evidence and there was some level of confusion. I wouldn't be surprised given how complex it sounds. So what is that? I mean, again, that's a recommendation for Boeing to go and look at and find out, well, why was it submitted for approval? If this is the Boeing engineering team supplying something for the approval of NASA and them to go, yes, it's okay to go flying, then we need to understand what was going on with that interaction. NASA approved, so they approved it. Let's just highlight these. So Boeing submitted it, NASA approved it. With incomplete verification evidence for Clause 9 Verification 1A. So would they have even been in a position to know that? Was it self-evident? Was it obvious? And again, who are the specific individuals involved with this? Were they given the responsibility to look for that and check that? If they were, then okay, why did it make sense not to do, to accept it, approve it with incomplete verification evidence? But if they're not specifically tasked to do that kind of review, or they don't have the resources to do that review, then we shouldn't be surprised that got through. But again, it shouldn't, as I understand from the previous sections in this report, it's not NASA's people's a responsibility to accept this stuff and point these issues out. When they get this thing, when they get these documents, everything should already be tickety-boo signed off. They're not part of the review process, as far as I can understand, and they're not resourced for it anyway. So, all of this emphasizes how important the roles and responsibilities are and how they're allocated, and the clarity of that allocation to make sure everyone understands their part in this process, the structure and how they fit together. I mean, this sounds like a complete breakdown. And like I said before, I wouldn't be surprised if there aren't many, many other issues waiting to be discovered and pulled out and dealt with. I'm assuming that that's what they're looking for now and addressing now with the ongoing investigations. Okay, the fault tolerance concern was raised to Boeing several times but was not addressed. Okay, so why was it not addressed? Where is the investigation recommendation to go and figure that out? Is that part of the Boeing ERCCA Enterprise Root Cause Corrective Analysis investigation? Early on, the Boeing mission operations ground rules and relationship with NASA created an environment where mission operation employees were discouraged from sharing key information with other NASA organizations, CCP Safety, FOD Safety, STRB. All communication was to go, right, okay. So that explains something. Okay. So this goes back to what we were saying up here. So if they're sending stuff here, let me use my pen. If FOD mission operations staff is sent, if FOD mission operations staff are sending stuff here, and they are told not to send stuff to here or here, that might well be perfectly fine, provided that Boeing engineering leadership do that activity. But if they're not doing that for whatever reason, then that would explain why they weren't aware of it. But again, it raises the question, why would you stop the mission operations team from providing that information around? Because surely all of those stakeholders need to know the status of the investigation, the status of the review, the status of the comments, and any issues that have been found. So again, this is a structural issue, which is undermined by the behaviour of some of these controllers. And again, I'm not picking on individuals here. I'm exploring this through the lens of a control structure. And this description is telling us that there are issues with the control structure and the behaviour of some of these stakeholders, some of these controllers. Okay. Oh, excuse me. I don't know why my phone is making a noise. Just bear with me a second. It was on silent. So why is it doing that? Anyway. Right, here we go. Recommendations. So implement a more rigorous process for NASA assessing Boeing HR verifications. So I think that's hazard report verifications. And again, this language and vocabulary, hazard report verifications. What are we talking about? Validation and verification? Are we talking about the review of these reports is a type of verification? What are we actually talking about here? This doesn't match my systems engineering sort of independent technical evaluation review mindset. Doesn't quite make sense. Work with Boeing to improve the process. Well, hang on a minute. Let's just start again. Implement a more rigorous process for NASA assessing Boeing HR verifications. I think a more rigorous process that's only part of the picture. What about the organizational structure and the decisions and responsibilities of the controllers involved? This is not just about a new or more rigorous process. There's much more to it than that. Work with Boeing to improve the process Boeing uses to verify HR controls, hazard report controls, or hazard risk controls, and their process for providing HR control data to NASA. Again, this is not about improving the process in isolation. There's much more to it than that. Ensure that safety concerns identified by the FOD mission operations team are communicated to Boeing and NASA. Again, the STRB board, I've thought, I would assume the responsibility for that includes this. It'd be interesting to know what the STRB board's roles and responsibilities are, whether they are explicitly laid out in some kind of process or procedure, and that it lists explicitly in there as part of the agenda for their meetings. One section of that meeting should literally be a list of safety concerns identified by whichever stakeholders, and who or what has responsibility for addressing those and providing feedback to closure. It's, the point I'm making is these recommendations, they're good, they're obvious self-evident recommendations, fantastic. But I don't think they go far enough. Even if you did these things, they would not solve these problems. I'm certain of that. Lessons learned. Performing a timely, in line with PDR Phase 1 safety review is essential. Well, yeah. Of course it is. In a time frame where design changes are able to be implemented to mitigate confirmed hazards. Yes, this is one of the reasons why I highly recommend STAMP and particularly STPA and STPA SEC for security issues, because you can apply those methods far earlier in the design process than you can with a traditional fault tree or failure modes and effects analysis. Now, of course, you can do fault trees from a functional perspective and identify common modes and all that kind of great stuff. But you should also have that supplemented with STPA. You would do far, far better including that in the process. Rigorous channelization is important to accomplish early in a design cycle. I don't know what that means. It does not make sense to me. What is channelization? I don't know. Question mark. What does it mean? Let's put a big question. What is channelization, everybody? Leaning into commercial practices does not mean that documentation shouldn't be clear and available. Well, that's debatable, because most commercial practices are not very clear and not very available. So, depends what you mean by commercial practices. It sounds like your expectations are too high. Maybe I'm just cynical. One core part of CCP success has been clear access to the data needed to make risk-informed decisions. STRB verifications data is another example of that importance. HR control verifications need appropriate level of rigor and awareness. Yeah, I mean, these are all like, yeah, we know. So why were they not done? If we all know all this, why was it not done in the first place? What is it about the control structure and the controllers that contributed to those things not happening? I can't help but think so far this has been quite superficial. I mean, it's good that they've captured this stuff and written it down, but we could go so much further if we were to start exploring the control structure. But I can understand that could be quite painful and a bit embarrassing, perhaps. But if we're going to prevent this kind of nonsense from happening again, we really need to get good at this stuff. We really shouldn't be shying away from really exploring. Okay, right, let's have a look. So what's this then? So this is helium. Oh, yeah, so this is, let's just zoom out a bit. So earlier in the report, there was a list of general findings, and it's called a matrix, and it's just literally just linking the topic to the particular issues. And so this is essentially, the helium failure tolerance topic. So if I line them up a little bit. Oh, there we go. So there's 3 issues there. In fact, I could use a nice yellow pen, couldn't I? There we go. Let's use yellow. So this one, this one, and this one. There we go. Yeah, so the safety accountability model, that's the thing I was moaning about earlier on that I just didn't think was adequate, and I think's caused a lot of issues. You could argue is related to this model and the way it's been implemented. Yeah, right, okay, so we've done that. So that is the end of the section on the helium system issues and the findings and recommendations and the lessons learned. The next topic is the helium seal material compatibility. So I think what we should just do is just take a 5-minute break, and then we'll come back to it. We'll continue with that. So I'll see you in 5 minutes. Hello, hello, hello. Welcome back. Just a short break there from this monster live stream. Let's make it sure it's working. Let's make sure the audio is there. Yes, it is. Look at that. Oof. Always get paranoid. Right then, where were we? So let's go back to here. Full screen share. There we go. So now we're going to talk about. Let's just zoom out back to the report. So we've just finished the helium system issues topic. So let's just move that down there. Put that over there so I know what I'm looking at. There we go. I've just realised I'm talking nonsense, aren't I? We've not finished the helium system issues yet. We've got a little bit more to run on it. So let's keep going. There we go. So helium seal material compatibility. Pardon me. So the service module propulsion system is designed with blankety blankety blank flanges that are not compatible with nitrogen tetroxide, which contributed to the helium leaks seen on the crew flight test. Okay, so let's just get our little jigsaw puzzle pieces. Let's get that one and that one. Let's put them over here. So let's have a look. So if the service module propulsion system is designed with something flanges that are not compatible, if this is the design, no, not this one. If this is the designer and they are providing the control actions to make the design, confirm the design, why would it make sense for them to do that? Did they not know that that was not compatible? Did they know it was compatible, but they made a decision, they accepted a risk, whatever criteria they used? Or was there something else going on? Why would it make sense for them to do that? That's what the investigation should go and establish. And that's hopefully what's going to be in this next section. So the Boeing Service Module Propulsion System CDR was held January 9-10, 2012 under the CCDev 2 contract. The helium pressurant system at the time specified something that would be compatible. Oh, interesting. That would be compatible with nitrogen tetroxide. By critical design review on the 11th November. The dates are so confusing. On November the 19th to the 21st, 2013, the system had evolved to only having a blankety-blank interface. The blankety-blank seal material was not identified in the CDR charts. The overall system design didn't change much. At the Delta Critical Design Review in 2015. Oh, so that is the Delta CDR is the Delta Critical Design Review, and that was held June 2015. So that was like 2 years, well, almost 2 years later. NASA did submit one RID. So a RID, let's have a think. What does RID stand for? I can't remember. It's a review item discrepancy or something relevant to material compatibility. So they did identify it. RID 194 only addresses short-term exposure. No mention on long-term compatibility will be addressed. So they knew about it. if we go back to our little mental model here, sorry, our little jigsaw puzzle here. So if this was the NASA reviewer, they provided a RID comment that said, hey, compatibility to the designer. So what did the designer do with that information? Why was that loop not closed? What was going on there? Why would it make sense? The RID was answered with a presentation highlighting, oh yeah, these are all blankety blank off the bottom, so you can't reference them. The RID was answered with a presentation highlighting a review of published papers and other data sources on the effects on individual materials. Flight-specific or assembled component testing was not performed. Oh dear, so testing was not done. And it was just a documentation review. And I mean, that might have... So if we're going back to the decisions, what was the mental model? What was the decision making? The designer might have been, well, we've looked at the documentation. The documents seem to say that it's okay, so it's okay. And then does that mean that they should not do a test? A representative test? Did somebody decide they don't need to do a test? I've seen that a few times in high stakes programs where they convince themselves that the paperwork is correct, and so that they're going to save some money by not doing a test, everybody. Yeah, let's make the project manager happy. Let's save some money in the project, instead of actually doing the test to confirm the engineering. Seen that a few times. I'm not saying that's what happened here, but, I wouldn't be surprised. So the CCTS 0208, so this was... Right, let's just jump over here a second. CCTS 208. There we go, that one. So that's 02819. Yeah, that one there. Cause 1. So that's cause 4, control 7. Whereas that one's cause 1, 13A. Hang on a minute. What's going on here? What's going on here? So CTS 08, that one is the same. That is different. Cause 1, control 3. CTS 1601, cause 3. That's not mentioned before, so that's different. Cause 4, that's different. CTS cause 5, that's different. Okay, so they're all different from what we've seen already. So these are different causes, different controls. So cause 1, control 13 references 1601 for material compatibility. 1601 0501 2017, that's that one there. Yeah, okay. Cause 1, control 24, that's different. Specifies that the helium system components are not compatible with hypers. So I'm assuming that's hypergolics. And references back to CCTS 208 again. Leaks at the RCS thruster mating flange. I wonder if that's supposed to be blankety blanked out. Just pretend it is. Just pretend that bit's blanked out. Were not looked at critically as a credible failure. Okay, so what we're saying then is the whole of this analysis, or these bits relevant to this, are just not good at all. So the creators of this stuff, the reviewers of this stuff, and then the independent reviewers of this stuff, there's 3 questions to be explored with regards to that. I wonder if it's copied and pasted from an original, another previous design, and they just didn't question it. I'm gonna play devil's advocate and ask a rhetorical question. I don't know, but I wonder if it's an existing design used elsewhere, and they've just copied and pasted it, and everything's fine because it's already flying, or it's already been, all the work's already been done, so let's just reuse it. I wouldn't be surprised if that's not the case. I've seen that a few times over the years, because the new people have no way to know. As far as they're concerned, the project managers said, "Oh, we've already done this before. Here's the paperwork. It's the same. Crack on." And so they've assumed it's all tickety boo. I don't know. So this one says the seals are assessed for compatibility and states this limits permeation through soft goods, but the environment isn't quantified, and the Control 3 verifications reference back to CCTS 1601 again. So there's loops and loops of. I mean, I've seen this kind of stuff happen. Infinite loops, and no one's sort of looked at the big picture and gone, well, this is not working. This doesn't work. It doesn't stack together. Or maybe somebody did do, and they just didn't have the time to update it. I don't know. The investigation should look into it. The CCTS 1601 Cause 3, orbital maneuvering attitude control, and Cause 4, reaction control system controls, reference from CCTS 0208 Cause 4, control verification set 3. All reference that materials are selected per Boeing's approved alternative standard DC. Right, so this is a standards document then. So that should be referenced. Section 413 from that document lists the material selection requirements, including short and long-term testing that is required to. So it requires testing that is required to simulate worst-case use environments. Long-term materials tests in the flight-like configuration were not performed. So they were supposed to do tests according to that document, but they've not performed them. So why would it make sense not to perform them? The helium seals were assumed to not be in an NTO environment. Permeation was not considered as part of the worst case use environment. Okay, so what? I mean, that's crazy. So how did we get in that situation? I refuse to accept it's human error and incompetence. I refuse to accept that. Something else is going on here. There's so many slices of cheese, so many dominoes involved in this. How did the structure contribute to this? Because if you got an assumption to not be in an NTO environment, that explains a belief, a process model, mental model. Permeation was not considered as part of a worst case use environment. Okay, so why? Long-term material tests in the flight-like configuration were not performed. So why? Why was that? What is it about the controller and the control structure that led to that? A helium leak was identified during the orbital flight test number 2 flight, but an IFA was not declared. See, that is not very good. That is really bad. Okay, so again, who or what was the controller? Why did they not initiate an IFA? Why would it make sense to do that? What's going on? And the next question is, for this thing, there wasn't an IFA. How many other IFAs were not raised as well that should have been? There's some really big questions now. I mean, there's been a lot of big questions already, but this is this is getting quite well. It's crazy. This issue was closed out, so the so the issues were closed out at a Boeing Prime Material Review Board without elevating to the NASA Review Board. Okay, so let's just let's say that this is the Boeing Material Review Board, and this is the NASA Review Board. Why would it make sense for the Boeing board to not provide that feedback up the chain? Were they requested not to do that for whatever reason? Were the procedures, was the contract, was the safety management system set up in a way that they're not supposed to do that? I mean, that was what was mentioned earlier on, wasn't it? The shared accountability model. And where was it? Where was it? Yeah, there we go. Discouraged from sharing key information with NASA organizations. All communication was to go through Boeing. Okay, so findings now. Findings section, everybody. Materials testing at the assembled component level was not required. As per standard 6016 or Boeing alternative standard. Individual material testing does not always capture integrated effects. Yep, that's the kind of standard system thing. It was assumed that the reaction control system flange helium O-ring, I get an impression that should be blankety blanked, don't know, would not be exposed to NTO. Even though it was on a common flange with fuel oxidizer and helium. So, why would it make sense to make that assumption? What is going on? With hindsight, we know it's an issue, but why did they decide that at the time? Was there a genuine reason for that? Yeah, I mean, is it? It's going to sound a bit of a silly question, but if it's not required if testing is not required per the standards, is there an implied assumption then? Is this implied assumption justified? Because maybe it's a case of, well, the standard doesn't require us to test it, therefore the standard is authoritative, and the reason the standard doesn't require it is because there's no exposure. So we're not going to test it because there's no exposure. Instead of, we test it to confirm there's no exposure, or we assume there is exposure and we need to see how bad it is. I don't know. This raises a lot of questions. It doesn't answer them. And again, this is an engineering issue that could affect many flanges, many O-rings all over the place. I mean, this is specific to the propulsion system, but how many other of this logical type of decision has been made on other subsystems around the spacecraft? I don't know. It's just doesn't make sense. Why would it make sense? hot fire ground test hardware was not torn down and inspected. Okay, why would it make sense not to do that? When parts of the test article were later disassembled after crew flight test, the O-rings were disintegrated. So they could have known if they'd have done that stripped down. So why was it not done? Why was it not torn down and inspected? Well, if if they assumed that there's no exposure and they're not required to test it, then I don't know. There's a big question here. The environment created as a result of hypergol permeation was not investigated, understood, or quantified. HR control just said limits permeation. Okay, so it was not justified. Helium O-ring was not assessed for hypergol compatibility. NASA did not have insight into the helium ring O-ring material selection. It was not included in the CDR, and even post CFT launch, there was uncertainty on what specific material remained. CCTS 0208 and 1601 repeatedly reference back and forth to each other, overcomplicating the picture of where and how controls were verified. Yes, I've had that exact same experience on very similar things. And it sort of seriously undermines your confidence in the people writing the reports. You know, are they actually taking care and due diligence to do the job and document it properly? Or is it just a badly written report? You know, because we're not here to point fingers and blame people. But at some point, when we're talking about engineering integrity and process and competence, if the reports are very bad and very complicated, then there should be efforts to address that. But again, I can appreciate if you're arguing with a program project manager that's like, well, it's just a document. You know, the document's just not very tidy because we've had to rush it. It's like, well, you know, come on, guys. We're supposed to have engineering rigor here. Let's make sure the documents respect that. I don't know. It's very difficult. This is not. There's so much more to this. I keep repeating myself. There's so much more to this than. Okay, right. Recommendations: perform component level materials compatibility testing for seal materials, ensuring that materials are tested in flight-like configuration with enveloping gas as liquid exposure, enveloping environments, and for enveloping exposure durations, including margin. Fine, yeah, great, okay, but what about integrated testing? Oh, why is it not working? Come on. Integrated testing? Question mark? Because we've set up here. There. That's it. There, look. Integrated effects, everybody. Integrated testing. Why is there not a recommendation to do that? Given we've just set up here, individual material testing does not always capture integrated effects. That's a recommendation we should be thinking about. The other recommendation is to get to the bottom of what the heck is going on with all of this. You know, to do with testing definitions, the test standards, the material compatibility, the scope of the testing, whether it's individual component level or integrated, why it wasn't torn down and inspected, you know, why the in-flight anomalies were not dealt with or investigated, you know, all of that good stuff. Lessons learned: tear down test articles and tear down test articles and inspect them post-test within a time frame that does not invalidate the inspection results. Fantastic. Why is that a lesson learned? Surely that should be a recommendation. Excuse me. Strengthen materials compatibility requirements for hypergol exposure. There is no substitute for long-term exposure testing. In the absence of suitable environmental testing, a material usage agreement is required to assess gaps. I would have thought that, and this is me just thinking out loud, if all of the space programs are using similar materials, then is there not like a high level materials compatibility and test and exposure program that captures these results and then shares that across the different programs so that individual programs don't need to do it themselves? I don't know. Is that a recommendation? I don't know. Is that a thing they do? I don't know. Did they used to do it and they stopped doing it to save money? And now we're reaping the benefits of that cost saving. There we go. Propulsion system components that are exposed to hypergolic propellants, including permeation through seals, should be required to have a long-term hypergolic exposure testing as an assembled component with encompassing environments applied. Material coupon testing is insufficient. I think it means component testing. Okay, so there's helium seal material compatibility. So let's just zoom up here. See if it's the same. Pardon me. Right, so it's that one, that one. Oh, it's exactly the same, isn't it? I don't need to do that, do I? Okay, fantastic. So that section is done. Now we're going to talk about the thermal issues. So let's just go back to our investigation report. So I've done the helium issues. Now we're going to do the thermal issues. There we go. Right. Of course, it's still all blurred out. There we go. Gosh, it's hot in my office today. Service module doghouse thermal issues. So this is 2 pages apparently. So you should be able to get through this. Oh, it's 4 pages. Let's have a look. We're making good progress today. We are making good progress. It is 20 to 7. So we've got about an hour and 20 minutes to go. Maybe we'll make it today. Maybe we will make it, everybody. Let's keep going. That's if I don't melt in my office. Right then, service module doghouse thermal issue. During crewed flight test, extreme reaction control system injector temperatures were observed and multiple service module RCS jets failed during the approach to ISS, leading to loss of 6 degrees of freedom control, which is very bad. That's like a very serious situation. Unexpected heating. So hang on, let's just get our little control loop. When we say unexpected heating, which control are we talking about? Are we talking about the designers? Their mental model is they've got an expectation for a level of heating and they've received feedback that shows, hang on a minute, this is a bit more than we were expecting. What is it about that? So unexpected heating of the SMRCS thrusters leading to thruster failures was observed on the OFT1 and OFT flight tests. Okay, so they've seen it on the OFT1 and OFT2 flight tests, but the hardware failure modes and temperature compatibility tolerance of the hardware components was not explored through additional ground testing, except for the pressure transducers and valve solenoids. The fact that the higher temperatures were resulting in deformation of the RCS thruster internal soft goods was not understood until ground testing was performed during crew flight test. Okay. The thermal environment understanding of the service module propulsion system dog houses during powered flight was primarily based on analytical methods. So the analytical methods was the feedback that explains the mental model of the designer, the decision maker. The most complete model was developed by Aerojet Rocketdyne and included the heating effects of the OMAC and RCS thrusters firing. Boeing also had a thermal model for the service module, which included a simplified model of the doghouses. But that was intended to address quiescent operations and did not include heating from firing the thrusters. The Aerojet Rocketdyne thermal model was validated for limited jet firing histories, as it was primarily intended to evaluate the temperature performance of the propellant tank and line heaters when the propulsion system was docked quiescent. The ability to maintain propellant temperatures above their minimum acceptance temperatures, as well as the commodity freezing point during the long quiescent period docked at ISS while using minimal electrical power, was a primary design challenge for the Aerojet Rocketdyne team and was the focus of ground and flight test objectives. The key aspects of that design challenge during quiescent operations were validated through vacuum testing on the ground and flight test instrumentation. The vehicle instrumentation within the service module doghouses was limited in the number of instruments and data rate. Instrumentation was primarily intended to validate cold performance or intended to support quiescent operations. Additionally, the flight vehicle's thermal instrumentation locations did not coincide with the locations of the ground test instrumentation during thruster testing. Oh my gosh. And the extrapolation of the thermal environments between the as tested and in-flight locations was not validated in ground testing. I mean, why would it make sense to do that? That's just blows my mind. There must be some reasons for it. It can't just be bad engineering. There must be some reasons for it. So what were those reasons? Because this is just... Let's just get our big model over here, everybody. So we've got... Let's just grab one of those. Go down here. Right, so we've got Aerojet Rocketdyne. I think that's what it is, if I remember correctly. AR. We've got Boeing. We've got the, where is it? Vehicle instrumentation. So the flight test instrumentation, vehicle instrumentation. I'll just put FTI, flight test instrumentation. I can't spell instrumentation. In fact, no, I'll use the actual labels because I'm potentially introducing some bias into this and confusion. Even though it might be easier for me to comprehend flight FTI, I shouldn't be faffing around like that. And that's a lesson for you when you're modelling as well, especially if you're not an expert in the domain that you are modelling. Try very hard not to make things easier for yourself at the sacrifice of maybe introducing biases later on. So there's vehicle instrumentation. So there's flight vehicle instrumentation, and I'll put flight, and then there's the equivalent ground. And there's an AR, there's a couple of models there. So there's the AR thermal model. And then there is the Boeing thermal model. All right, so let's just put these over here. Hang on. Let's put that there, put that there. Right, 1, 2, 3, 4. 1, 2, 3, 4. Copy, paste, put them over there. FTI, FTI, put them over there. Right, so let's right, let's move that out of the way. Right, let's just have a look a minute. So our control process is I'll zoom in a bit. Our control process is the flight vehicle, either in its ground test environment or in the real flight test. And so they've both got flight vehicle instrumentation. So I'm going to call those ground and flight. So they are my sensory feedback, you might say, in my control loop. And then that goes back to Boeing and or Aerojet Rocketdyne. And then they have some models. And those thermal models are essentially a type of process model. Let's just make those smaller. There we go. So that's where they would fit in there. So this sensory feedback is been provided into these models, and Boeing and Aerojet Rocketdyne are making decisions based on those models. But there are some significant assumptions and limitations in the data provided for those models, and they're not consistent. In fact, actually, I mean this model, this picture here is just, it's an incomplete model and it's not appropriate for this particular example. But I'm just trying to get you to think about. Let's say that this is. Let's say for a minute that this is Aerojet Rocketdyne, and they're imagine. In fact, actually, why don't I just use this over here? Yeah. Let's imagine that loop is Aerojet Rocketdyne, and there's the flight test instrumentation. So they're happy as they are over here doing their flight test. This is their ground test, and I've used the wrong one, haven't I? I needed that one. There we go. So they've got their flight vehicle instrumentation ground, doing a ground test, providing feedback to a thermal model, and then they make decisions and do things based on that. And then if you imagine that there's an arrow that goes from here. Why is it doing that? I want a straight line. And I want it to go from, yeah, let's just do it from there. Why not? And this goes all the way over here to Boeing, and that informs the Boeing thermal model that they're using. So that would explain why they've made the decisions that they have. These models across the control structure are inadequate, inconsistent. But again, the intent to keep those consistent, I'd argue that this is something that, competent engineers and organizations would know that they need to do that. And so I'm assuming that they're all competent engineers. So why would it make sense for that not to happen? What's happened? What's going on with the individuals, the organizations, the contracts that they have to share data? What's going on there? Why would it make sense for them to behave this way? This is not just about competence. It's not about stupid humans and human error. Something else is going on here, and we should be looking into why. And again, like I said earlier on for the other topics, if they've got this issue in this area, how many other areas on the spacecraft in the design do they also have similar problems, similar challenges? I would argue that it's not isolated. Okay, so prior to... and then the other thing is about this prior to... orbital flight test, OFTs. So there should be a run-up to the OFTs where they decide what evidence do we need to go flying, and have we got it from the tests, ground tests, representative ground tests, all the other good stuff. How they track assumptions, what test points they're going to test, what the reasons are, how they're going to collect that data, how they're going to validate it, how they're going to be sure that it's the right data, verification and validation. And then how are they going to instrument the real spacecraft? And is the instrumentation and data rate and everything else actually acceptable? And if it's not, why would it make sense to go ahead anyway? There's so many questions to be answered. So prior to the OFT, orbital flight test, NASA engineering evaluated hang on, let's just yeah. Right. So prior to OFT, NASA engineering evaluated the issues with the qualification testing of the service module propulsion system thrusters and noted that the results of the ground testing did not fully satisfy verification expectations for flight, representative usage-induced environmental conditions. However, NASA engineering recommended proceeding with the OFT flight. As they assess that low risk exists for all mission failures. Okay, so if they recommend proceeding and they've done an assessment, they've made a decision that the risk is low, then how have they arrived at that decision? I mean, that's a different sort of focus of the investigation in its own right. And propose that the data obtained from that flight be used to validate the acceptability of the thrusters for the eventual crew flight test. I mean, that might be perfectly reasonable, but it makes assumptions that in the previous few paragraphs have shown to be incorrect, invalid assumptions. During OFT1, 10 RCS thrusters failed off during the brief unsuccessful test flight. I mean, that's quite a few. The 10 failed thrusters included 6 of the 8 aft-facing thrusters. The extremely rapid SMRCS jet firings, which occurred early in the flight test, led to a number of jet firings being far in excess of qualification levels and resulted in RCS failure annunciations by the FDIR. Okay, so again, was that intended or was that accidental? What was going on there? These rapid jet firings also led to thruster heating far in excess of qualification level test levels. Of the 10 thrusters that failed off in flight, 9 were shown to be due to transducer failings triggering FDIR, and 1 thruster had a transducer failure and another hard failure that caused the thruster to remain inoperative after the other thrusters were re-enabled. The hard failure was believed to be due to the valve solenoid overheating. The limited reaction control system hard failures experienced during OFT1 led to a false belief that the thruster hardware was very robust for exposure to high temperatures, except for the transducers and solenoids. This belief persisted until the ground test results were available during CFT. Okay, so yeah, going back to our little model here, their models, their beliefs were that it's A-OK until they got contrary evidence. But it was during the crewed flight test, not before the crewed flight test. During OFT number 2, 2 of the 8 facing service module reaction control system thrusters two of 8 failed off during the approach to the ISS. These 2 thrusters were reselected and performed during the deorbit burn. 1 RCS thruster experienced a single FDIR failure during ISS approach and subsequently failed during the deorbit burn. 2 of the 3 failed jets had fuel injector temperatures observed at or above X degrees Fahrenheit in telemetry, and S1A1 and B1A3, and the 4 thrusters with the highest oxidizer injector temperatures were aft facing, including the 3 mentioned above. The heating related fault tree block H317 hot valve injector was identified as a hot valve injector was identified as a contributing factor for the B1A3 and S1A1 failures, but not the S2A2 failures because the injector temperature never exceeded blankety blank. Seat swelling was considered, reducing propellant flow, but since flow is controlled by trim orifice and injector, seat swell contribution to resistance change will be negligible. But the high injector temperature was theorized to result in NTO bubble formation. The corrective action identified to mitigate the risk of further failures on the crew flight test was a mission data load change to the blankety blank to reduce the potential for false failures due to the limitations of the thruster chamber pressure sensor sample rate. Thruster chamber pressure sensor. OFT2 service module reaction control system jet fail off non-conformance. Francisco Fuser 15th December 2022. So this was before the flight test. I'm surprised that wasn't blankety blanked out. Maybe it was supposed to be. Apologies, Francisco. OMAC thruster heat soak back into SMRCS jet hardware was observed on OFT2, but was not deemed to be as significant as the heating produced by the firing the RCS jets. So heat soak back and firing the RCS jets. RCS thruster injector temperatures during soak back appear to have exceeded temperatures observed during qual. So that was 2023. Right, findings. During driving thermal design concern for the service module doghouses was maintaining propulsion system temperatures using heaters during quiescent operations. So there's an important constraint there about maintaining propulsion system temperatures. so they don't get too cold. The Aerojet Rocketdyne thermal model was validated for quiescent operations by ground testing. The model included the effects of jet firings, but these effects were not validated by ground testing. So, like I pointed out over here, there's a question then over the model that they've used and the quality of it, whether it's representative or not. So whoever or whatever is involved in that activity, the investigation needs to go and look at, well, how do they manage their thermal models? Because again, this could be a systematic issue for Aerojet Rocketdyne to deal with. I'd argue they have lots of customers, and this is about engineering integrity and how they do their thermal modeling, how they verify and validate it. So there's potentially a really important task here for them to go and look at. The same again for Boeing and how they manage their models and satisfy themselves that they are adequate and appropriate for what it is they're doing. And then, of course, there is a question there over how those models are justified and validated to NASA, if they are to accept them or not. There we go. So NASA Engineering submitted a Boeing RID comment during a propulsion system design review in the SAA timeframe that the AR thermal model was immature. So they've said it's immature. So they knew this. This was in the early days. So this is the SAA time frame. So let's just zoom to the time. Is it this one? Yeah, there we go. Look. So during this time period, there we go. I can't draw straight. There you go. From there backwards, the SAA time period. Where is it? There we go. SAA time frame. That the Aerojet Rocketdyne thermal model was immature. The RID comment was withdrawn to be discussed at a later technical meeting. No evidence of resolution was found. Oh dear. So it's one of those, isn't it? I mean, I have to implore to everybody watching this, when you're involved in stuff like this, it is a pain in the backside, but it is so important to keep a written a log or a journal of what the topic is, when it was discussed, and what the timeline is for that topic until it's closed off and the loop is closed. Just for your own sanity, really, but also so that you can make sure that it's adequately addressed in the various administrative systems of the program. You know, if, like, for example, the RID comment, the RID comment was withdrawn to be discussed at a later technical interchange meeting. So yeah, I mean, that might be the appropriate thing to do, but the comment should be graduated into a task management system or an issue tracking system, not just managed locally. It should be, available for everyone to see. I'm not saying it's easy to do. It's bloody not. It's really hard, especially on a complex, fast-moving program. But again, this is where senior leadership should be providing tools for their workers to be able to manage this level of complexity and detail. And often they don't. I mean, I've seen some organizations just have a basic access database in this century. Is that really appropriate for the complexity of the program? Anyway, right. Boeing thermal model did not include the effects of jet firings before CFT. Why would it make sense for Boeing to do that? Who was in charge of those models? What organization? How were they documented? You know, the assumptions, the limitations, any outstanding actions, how was that managed? RCS thruster testing configuration was not flight-like, as it did not reflect the insulative properties of the doghouse assembly, and included, active cooling to reduce the turnaround time between tests. Oh, right, so it was optimized for, reduce the turnaround time between tests. I mean, I'd argue that the people involved in designing the test rig and doing all of that stuff, if they know that including active cooling reduces the turnaround time between tests, what consideration did they give for upsetting test integrity? Did they consider it? I assume they would, but I don't know. All of this stuff that we've read so far just, it is really, really odd that they would behave this way. So we need to understand why. Just me saying it's odd is, we need to understand why it made sense. These are not stupid people. These are high caliber people. They're the kind of people you would want on the program. So why would it make sense for them to behave this way? Okay, let's just check that my audio is still working. There we go. Bit of a feedback test, dormancy check. So the SM hot fire test was not intended to evaluate the thermal environment within the doghouse. The test article did not include all of the OMAC and RCS thrusters, nor were the few RCS thrusters that were included in the test article fired for flight-like durations. So why was it so unrepresentative? Or maybe it was so unrepresentative to start with, and then they just haven't updated it when it needed to be updated. Why is that? Flight instrumentation locations for thermal sensors were limited and different than the locations for the RCS thruster ground testing. Explicit flight test objectives exist for determining the local crew module thruster thermal environments, but there were not analogous flight test objectives for the service module thrusters in the doghouse. Okay. So why were there not any flight test objectives for that? I mean, it seems like a logical thing that you would have. So why didn't they include it? What is the controller? What is the process involved in creating flight test objectives? And why did that process not pick up the need for flight test objectives for the service module thrusters? Is it a different part of the organization? Is it a different stakeholder? What's going on there? It always boils down to who or what is the controller? Who or what is their control process? What are the control actions they need to provide? In this case, it is defining the flight test objectives for this bit of kit, whatever it is. So who or what is that? What decisions did they make? What beliefs did they have? Why would it make sense not to have flight test objectives for these service module thrusters? The investigation should figure that out. OFT1 and OFT2 in-flight anomalies investigations noted high temperatures. Okay. OFT 1 and 2 investigations did not include ground testing of doghouse assemblies or RCS thrusters to better understand the thermal environment during OMAC or RCS thruster firings or soak back heating after firings. Okay, so these are questions about the integrity and method of the OFT1 and OFT2 in-flight anomaly investigations. And I've already talked a bit about that. Please use stamp and cast, please. You would do so much better. Anyway, unexplained anomaly and fault tree dispositions. For the service module reaction control system thruster in-flight anomalies were not validated through subsequent ground testing. Thermal and propulsion disciplines were not well integrated before crew flight test. Okay, I mean that, there we go. So if we had a control structure for thermal and propulsion and they're not well integrated, well, that would explain a lot of this. Okay, so is the first recommendation to integrate them? Is that the first recommendation? Let's find out. So, conduct ground testing. Yeah, okay, fantastic. Of the doghouses in their flight configuration to validate the thermal models. Pardon me, when the OMAC and RCS jets are firing, as well as soak back, I would suggest. Update the Aerojet Rocketdyne and Boeing thermal models as needed based on the ground test results. Update the service module doghouse thermal environments as needed based on updated thermal models and ground testing. Recertify the service module RCS thrusters and other hardware within the doghouses for the revised thermal environments. Increase the number of in-flight thermal measurements within the doghouse on Starliner 1 service module and validate the updated thermal environments through formal flight test objectives. Yeah, I mean, there is a recommendation to ensure that the ground and flight test, instrumentation is representative of what needs to be measured. There must be representative, and of course, the data that they get from a real mission should be used to validate the models, or if there's an issue with the models, find out what the issues are. Okay, right. Lessons learned. Document the limitations of vehicle thermal models for both hot and cold cases. Yeah, fantastic. Kind of, that's what they should be doing. Why weren't they doing it? Invest in ground testing to validate critical models, particularly when flight experience or in-flight anomalies show that induced environments are exceeding pre-flight expectations. Yeah, absolutely fine. But why is it taken this incident to do that? Why wasn't this already in action, or was it already in action in place? And for whatever reason, they just didn't do it on time. Ensure flight test objectives address hot and cold cases for propulsion systems. Fantastic. Okay, so let's just have a look at this. So this is the same as the thing we were looking at earlier. So let's just have a look. There we go. So we've got, yeah, all the same. Fantastic. Right. Great. So the next bit is the thermal thruster failures. So we've done thermal. Let's do the thruster stuff. So I think what we'll do is, it's now 7:15. So I think what we should do is probably just have a quick 5-minute break. I think that would be good. And then we can pick up in 5 minutes. So just bear with me. Hello, hello, we're back again. Audio levels going up and down. Fantastic. Right then, let's continue where we left off then. So we just finished talking about thermal stuff, and now we're going to talk about thruster failures. So we're going to do this next part here. So we're at page 259, and the report goes to 299, but I think a lot of it is redacted in the latter section. So yeah, I think we're getting there slowly but surely. Pardon me, this section is 3 pages, and then it's a big chunk with lots of redacted. So yeah, we should get through this now. Right then, here we go. Let's zoom in. Why is it jumping around? There we go. There we go. Right, RCS, orbital maneuvering and attitude control thruster failures. So during CFT, extreme RCS injector temperatures were observed, and multiple RCS jets failed during the approach to ISS, leading to loss of 6 degrees of freedom control. So that's like one of the worst hazards you could have. Really bad. Ground testing and teardown of the RCS thruster identified that there was deformation of the Teflon RCS poppet seal occurring. SMRCS thruster failures were observed on the OFT-1 and OFT-2 flight tests, but the hardware failure modes were not explored. Through additional ground testing, except for the pressure transducers and valve solenoids. that higher temperatures were resulting in deformation of the internal soft goods of the RCS thrusters was not understood until ground testing was performed after additional failures were observed during the Starliner approach to the ISS during the crew flight test. So there's so many things that have gone wrong here, and also potentially so many things that have gone right. Why would it make sense that this would happen? So before they went flying in the first place, certain things should have been done. So why were they not done? Or were they done and they just didn't deal with the results properly? And then post the orbital flight tests, why were the hardware failure modes not explored through additional ground testing? So there's so many open questions. CCTS 1601 cause 4 RCS controls reference that materials are selected per Boeing's approved alternate standard. Section 413 from that document lists the material selection requirements, including short and long-term testing that is required to simulate worst-case use environments. Long-term materials tests in the flight-like configuration were not performed. Okay, so is that 1601 cause 4? Have we already seen that? 1601 cause 3. Oh, cause 4 is there, look. RCS controls. Yeah, there we go. Okay, and this document DCC 12001F. Is that the same one we saw earlier on? Yeah, that one there. There it is. Okay. So it's the same issue, similar issue. So that standard, essentially that standard is behaving as a controller. Arguably it is behaving as though it's a controller. And that is influencing the behaviors of the controllers below, the stakeholders below. The vehicle instrumentation within the dog houses was limited in number of instruments and data rate. The primary indicator of thruster failures were the chamber pressure measurements, which has a blankety-blank data rate. Prior to the orbital flight test, NASA engineering evaluated the issues with the qualification testing of the service module propulsion system thrusters and noted that the results of ground testing did not fully satisfy verification expectations for flight representative usage induced on environmental conditions. However, NASA engineering recommended proceeding with the OFT flight as they assessed that low risk exists for all mission phases and proposed that we use the data obtained from that flight to validate the acceptability of the thrusters of the event for the eventual crew flight test. So that's the same sort of comment as made earlier on, isn't it? So where is it? Yeah, there it is. So this topic here is the same as this bit here. Exactly the same. Well, they do look slightly different. It's very slightly different. propose that we use the data obtained from that flight to validate the acceptability of the thrusters for the eventual CFT. So they are the same thing, but they're written very slightly different. We use. Anyway, during OFT 1:10, so it's the same text. 6 of the 8, the extremely rapid SMRCS firings which occurred early in that led to a number of jet firings being far in excess of the qualification levels and resulted in the RCS failure enunciations by FDR. These rapid jet firings also led to thruster heating far in excess of test qualification levels. Of the 10 thrusters that failed off in flight, 9 were shown to be due to hang on, I'm going to have to do this. Let's just do this. There we go, because this is getting a bit difficult now. Right, there we go. You might not be able to see this because it's a bit small on the screen, but what I'm just trying to understand is there's 2 sections of the report that's essentially got copy and paste in it. And I don't know whether that's just because that helps with explaining things. If you just read the specific section you're interested in, you need the same context, or whether it's just an editing issue because they've done it fast. I don't know. And I just want to make sure I'm not missing anything. So let's have a look. So where are we? Let's just put a line. So due to transducer failures, there we go. Hang on. Pen. Why is it? Oh, it's because I've got 2 different pens, isn't it? That's why. Right. Due to pressure transducer failures triggering FDIR, and 1 thruster had a transducer failure and some other hardware. Oh, that's different. There, look. Hard failure that caused the thruster to, remain inoperative after the other thrusters were re-enabled. So that's the 1 word difference between this one and this one. The hard failure was believed to be due to the valve solenoid overheating. The limited RCS hard failures experienced during OFT1 led to a false belief. So that's exactly the same. And I keep clicking on the wrong one, don't I? False belief that the thruster hardware was very robust for exposure to high temperatures, except for the transducers and solenoids. This belief persisted until the ground test results were available during OFT. Okay, so it's like the same text, and then the next bit, that looks exactly the same. 2 thrusters were reselected and performed deorbit burn. 1 thruster experienced a single 2 of. Yeah, it's the same text. 2 of the 3 failed above telemetry. The highest oxidizer inject temperatures were, I know, I've just had an idea. What if I did that instead and then stretched it to there? There we go. That's better, isn't it? Right. So B1A3 S1. So that bit and that bit the same. Injected temperature never exceeded blankety blank during ISS approach. So that bit's different. So it's not there. Seat swelling was considered reducing propellant flow. But since flow is controlled by the trim orifice and injector, seat swell contribution to resistance change would be negligible, but the high injector temperature was theorized to result in NTO bubble formation. The corrective action identified to mitigate the risk of further failures on CFT was a mission data load change to the, oh, here we go, look. Oh, blankety blank, everybody. Persistency. Right. Right. Okay. So that's a bit of a boo-boo from an information control perspective. So this blankety blank bit is essentially this bit down here. So obviously I'm not going to read it out, but you could we could guess, we kind of guess what it is. You know, a candidate controller in the control structure will be this. And so the corrective action identified to mitigate the risk of further failures on the crew flight test was a mission data load changed to the blankety blank persistency, whatever that is, to reduce the potential for false failures due to limitations of the thruster chamber pressure sample rate. Okay, so that sounds like this blankety blank was interpreting some sensor data, and that led to false failures, which is something we've already talked about earlier on. So if you think about the where's the jigsaw piece, everybody? I had one around here somewhere. Where have I put it? There it is, that one. Let's take that one down here. Let's put it there, and then let's make this bigger and this bigger. Right, so if you imagine that there's this blankety blank controller that we don't know the name of, whatever we can imagine it is, we know it controls something, and we know logically it's got a process model about something, and we know logically that that process model will be updated by some form of feedback, sensory feedback. And so if this blankety blank controller is receiving some blankety blank feedback, and it makes decisions based on that faulty feedback, then of course, what do we expect? So I can understand why that would be blankety blank. So obviously I'm not going to say anything more about that, but suffice to say, if you were to use STPA, you could anticipate these kind of issues and address them in your design, either eliminate them or include some kind of mitigation, response and recovery to it. So yeah, if I was involved in that part of the analysis of the design, we'd certainly go a lot deeper and be able to eliminate, I would expect, a lot of these issues. Maybe it might drive a slight change to the sensor feedback architecture. I don't know, maybe. But I can understand why that's blankety blank. Say no more, say no more. Wink, wink, nudge, nudge. Right, anyway, OMAC thruster heat soak back into the SMRCS jet hardware was observed on OFT2, but was not deemed to be as significant as the heating produced by firing the RCS jets. Even though, hang on a minute. Oh gosh, here we go. Let's do that. There we go. Let's put that down there like so. Stretch it out a bit. Right, where's this? There we go. So is that the same as this bit? Yes, it is. There we go. So OMAC thruster soak back. OMAC thruster heat soak back. And that's the same. Yeah, that's the same email. So that's exactly the same. I'm a bit confused though, because this bit is supposed to be about service module OMAC thruster failures. And this bit is about the doghouse thermal issue. I'm a bit confused. I'm not completely convinced these two sections are as detailed as they should be. I think there's a bit of copy and paste gone on, and I'm not quite convinced they properly address the thermal doghouse issue or the thruster failures themselves. Because there's the thruster failures, that the actual thrusters themselves and their failures, and then there is the control of those thrusters and issues with that control. And thermal issue is just a subset of those issues. Does that make sense? So if you're thinking about, let's just get our little jigsaw puzzle piece for a minute. So if you're talking about issues with thrusters, the control actions, the control path, the thrusters providing thrust, you know, the first thing is, well, is there an issue with the control path? And in this case, we say, well, there's temperature issues. Okay, great. And material compatibility issues. And then we're talking about, well, is there any questions over control? And that bit that was blankety blanked out implies there were some issues with control as well, based on sensory feedback, inadequate sensory feedback. So there are, logically, like from an STPA perspective or a CAS perspective, we would always start by being clear about what are the control actions we're interested in. And because we're doing a retroactive consideration, it's more about, well, what are the contributory control actions to this situation, which are logically the same as unsafe control actions. But of course, we're looking at it with the benefit of hindsight. So what are those control actions? Why are they contributory? What is the context within which they are unsafe? They contributed to the outcome. Who or what is the controller? What decisions are they making? What is their control algorithm? Or ithms, because there's probably many. What are their beliefs? What is the process mental model? Logically, what is the feedback? What are the sensors involved in that? How is that contributing? And of course, are there questions over the control process itself? And I suppose material compatibility sits firmly in that box, though you might argue it's part of the control path, but that's a bit of an academic conversation. But what I'm saying is, when you think about things through the lens of these loops, you can structure the way that you do your analysis, and it gives you a framework to work to, so you don't get lost and you don't miss things or copy and paste stuff which seems to be relevant but actually doesn't quite address the appropriate parts of the control loop. But again, I suppose I'm a bit of a layperson in the respect of this subject matter. So maybe I'm seeing issues where there are none, and it makes perfect sense to those that are not lay people, so to speak. Right, so the findings. So that's the thermal issue findings, and they start there. Oh, so they are different. Yeah, so that is different. Fantastic. So it's not a copy and paste error on this bit, and it's probably not a copy and paste error on the other bit as well. Okay, good. Fantastic. Right, well, let's make the screen bigger and we will continue. So findings then. And this is, just to emphasize, this is the service module reaction control system, orbital maneuvering and attitude control thruster failures. So findings, design details and the internal configuration. Oh my God. Design details and internal configuration of the RCS thruster valves was not fully documented in data deliverables to NASA, nor was it readily accessible to NASA engineers as inside data. So it must have been somewhere, presumably. It just wasn't available to NASA. Is that what they're saying? Orbit insertions and ISS approach trajectories were not fully defined, and the resulting RCS thruster duty cycles were not fully understood when the thruster qualification testing was defined and performed. Okay. RCS thruster configuration testing configuration was not flight-like, as it did not reflect actual duty cycles predicted for crew flight test. RCS thruster testing configuration was not flight-like, as it did not include insulative properties of the doghouse assembly and included active cooling to reduce the turnaround time between tests. Limitations in flight measurements and data rates made troubleshooting of the RCS thrusters very difficult. The extremely high usage rate of the RCS thrusters, overheating the pressure transducers on OFT1, was attributed to be the cause of numerous failures identified by the FDIR. So that one, I think, refers to the blankety blank thing that was not covered up, but was covered up, if you know what I'm talking about. So on OFT1, numerous failures identified by FDIR. They may have been put down to overheating the pressure transducers, and actually it could have been due to overheating the pressure transducers, but it could also be a controller issue. The controller itself is giving an indication that they've got these FDIR issues, and it could be related to this coincidentally, but also it could not, it is possible, how can I say this? There is a potential logical scenario where it's not due to those temperature sensors. It could be due to the blankety blank controller doing it itself for whatever reason. That's very interesting. I'm not saying it is that. I'm just saying using STPA, that is one of the set of causal scenarios we might want to think about. And I imagine that's why that bit has been blanked out of the reports. I imagine perhaps that maybe this investigation report is focused on the mechanical, physical hardware, and issues to do with the control systems are not in these reports. They're dealt with separately. But again, STPA and CAS could find both of those sets of issues. Okay, right, where were we? So, extremely high usage rate of the thrusters overheating the pressure transducers on OFT1 was attributed to be the cause. So it was to be the cause of numerous failures identified by FDIR. That is one set of causal scenarios. There are others that don't necessarily involve the sensor feedback part of the loop. RCS thruster performance after thruster reselection on OFT1 gave Boeing and NASA team a false sense of thruster capability robustness. OFT1 and OFT2 Orbital Flight Test 1, Orbital Flight Test 2, in-flight anomaly investigations noted higher than expected temperatures were measured at the RCS thruster injectors. MUAs were not generated for the RCS thruster soft goods. Right, stand by while I figure out what MUA is, because I cannot remember. Stand by. Where's the report? There it is. Right. MUA, everybody. MUA. Material usage agreements. Are we sure that's what we mean? Yes, it is. Material usage agreements. Right. So material usage agreements. Let's take that one down here. Flight management computer FMC MUA material usage agreement. Is that right? MUA material usage agreement. Fantastic. Let's just put that to one side. We're not generated for the RCS thruster soft goods. So again, a controller, some controller of some kind, is responsible for doing that. So if they weren't doing that, why was that? There might be a good reason for it. And again, that's not even mentioned in here for some reason. It's mentioned in the helium compatibility section, but it's not mentioned. Yeah, I don't know. It's weird. Don't know. Anyway, only flight hardware assigned to subsequent flights was available for testing. During the flight test program. I mean, again, who or what is in control of assigning hardware to the flight test program versus the ground test program? Because you need to do ground testing before you do flight testing. So, yeah, who or what is involved in that, making that decision? And why was it accepted? Surely the safety review board would have been like, no, you're not doing that. Did they even know? NASA didn't foresee the poppet extrusion problem, even though it was a known failure mode and identified on the OFT2 flight, OFT2 fault tree, but was closed as a non-credible scenario. Oh gosh, right, okay. So that whole review and acceptance activity of that fault tree for that particular scenario should be torn to pieces to understand what they mean by non-credible scenario. And now wherever that is addressed in any fault tree involved in similar or the same designs, same systems, that needs to be corrected. So there's a recommendation there. Gosh, it's hot in this room. Right, for OFT2, NASA and Boeing didn't have the tools to measure thrust degradation. Simply treated thrusters as failed or operation. Why would you do that? Why would it make sense to do that? Why? So they didn't have the sensory feedback path adequate to assess thruster degradation. So why would it make sense that they've got a design, a control loop like that, and why it was acceptable? And when I say why does it make sense, and I keep saying that over and over again, it's because I want to embed in us that we shouldn't just immediately jump to the apparently logical, obvious, trivial solution that everybody is stupid, everybody's incompetent, they didn't do the job properly. We should resist, absolutely resist jumping to those kind of conclusions because it's not helpful. It undermines trust and it undermines credibility in the investigation. We have to ask the question first. Try and short circuit our little brains as investigators. Why would it make sense for them to behave that way instead of everybody's stupid, everyone's incompetent? We've got to stop doing that. We've got to avoid jumping to the cause, jumping to root cause, or what we think is the root cause because it's so obvious and we're really clever because we're investigators. No. We need to resist that. So why, ask ourselves the question, why would it make sense for them to behave this way? And it may be, once you've asked that question and established what's gone on, what is the control structure, what are the interactions, it is possible that maybe there is a level of incompetence involved, but that's not where we should start from. We should start from, these people are experts, they're competent. What is it about the situation they found themselves that led to the situation we've experienced? Why would it make sense? Gosh, it's hot. Right. OFT1 and OFT2 in-flight anomaly investigations did not include ground testing and teardown of doghouse assemblies or RCS thrusters to better understand the impacts of thermal environment on the hardware and soft goods. Okay. UA. Oh, what is UA? UA. No, of course, we're not going to find it like that, are we? UA, there it is. Unexplained anomaly. I knew it was something like that. Unexplained anomaly, blah, blah, blah. There we go. Unexplained anomaly and fault tree dispositions for RCS thruster in-flight anomalies were not validated through ground testing. Okay, why? Why did it make sense not to do that? Okay, recommendations. And I banged on about this last time. Please, when you're doing your investigation reports, give your findings, recommendations, actions, whatever it is, give them a unique identifier and allocate them to a particular, stakeholder. Do it in a table, whichever's easiest, just so that it's easier for the reader, the audience, to see whether we've got a good set of recommendations, and that if there are findings, that it's obvious which recommendations relate to which findings. Because just chucking them in a bulleted list is not really very helpful. But I do appreciate that everyone's been working really hard to do this and doing it really, really fast and everything else. So I'm not trying to be critical of the people that have done this, but for you, for future knowledge, please make them, give them a unique reference so that you can track them and keep track and make sure they're closed properly. Okay, right. And of course, if there is a finding, that it's obvious that there's an associated recommendation to go with it. Because if there is a finding, the next question is, well, so what? And then, now what? Okay, recommendations. Conduct ground testing. I think these are the same as the other ones, aren't they? Let's just put this down here and have a look. Let's just minimize that out of the way. Stretch that over there. So these are the recommendations. Can you see that? Is that big enough on the screen? Let me zoom out a little bit. There we go. So, conduct ground testing of the SMRCS thrusters in their flight configuration to validate the most likely failure causes and RCCA fault tree closures. I don't agree with that. And I think they need to be tested, but I think it's more than most likely failure causes and RCCA fault tree closures. I would be concerned that there are more than just failures involved in this situation, and that blankety blank flight control, whatever it was called, that thing there that I can't be named because it's blankety blanked out in the previous section up, I will be concerned there's issues with that as well. And using a control loop, using STPA, using CAS to understand that, I think would be far better than just focusing on failures and fault trees. I think I would, given the severity of what we're talking about here, I would strongly recommend that. And obviously, I've been recommending that for the last 29 live streams, but I think this is where it really matters as well. Okay, conduct ground testing of the SMR RCS thrusters in their flight configuration. So it's the same as the above. In their flight configuration to requalify the propulsion system for the anticipated thruster usage and induced environments. Yeah, again, please use STPA to clarify the design and the issues with non-failures. Pardon me, dangerous successors, because I will be concerned there's some issues with that in there as well. Conduct a teardown and inspection of ground test articles within a time frame that does not invalidate inspection results to understand any changes, damage resulting from the updated qualification test program. I think we've already seen one of those, haven't we? Conduct teardown. I thought we'd already seen that already somewhere. Conduct teardown. Oh, there it is, teardown. So tear down the articles, conduct a teardown, an inspection of ground test articles within a time frame that does not invalidate inspection results to understand any changes, damage resulting from updated qualification test program. Yeah, absolutely. Because you'll do your new qualification test program, and there's a potential you could damage, the test articles. So you want to make sure you're not doing that. Generate material. What's it called? MUA. Come on, Sai. MUA. Material usage agreements for the RCS thruster soft goods, and generate. Excuse me. And as needed. What? Generate MUAs for the RCS thruster soft goods and hardware as needed to address material compatibility and revised thermal environments. Increase the data rate. Increase the data rate of chamber pressure measurements on the Starliner 1 RCS thrusters. Right, if going back to what I said earlier on about this blankety blank thing that's mentioned here, flight management computer persistency, to reduce the potential for false failures due to the limitations of the thruster chamber pressure sensor sample update. That strongly sounds to me. Let's just put this over here. And then what we'll do is we'll put, is it combustion chamber? Thruster chamber pressure, thruster changer pressure, changer. Gosh, it's been a long day. Thrust chamber pressure. And then we have pressure transducers. Everybody, thruster. Where is it? Thruster chamber pressure. Chamber pressure sensor sample rate. Chamber pressure sensor. And then we've got sample rate. So let's just make that a bit smaller. Put that underneath. Make that centered. There we go. Look at that magic. Right. Can you see that all right? Let me just make that bigger so you can see. Right. So imagine for a minute you've got this thing called a blankety blank. And it has its control process is obviously the thruster chamber pressure. And it controls that through some form of control actions, including valves and all of that exciting stuff. And then it's got a pressure sensor or sensors. I don't know how many there are. I don't know if there are any diverse ones. I don't know if it's single or dual or whatever it is, but there's a sample rate. And that provides information about the pressure ramp up and ramp down, whether it's continuous, whether it's low, whether it's failed, whether it's assumed to be on or off. There was a mention earlier on about on or off, wasn't there? Where was it? It was down here somewhere, wasn't it? Hang on a minute, where was it? On or off? There was a mention about it. Where was that? Hang on a minute. On or off? Let me search for the word off. Off, not office, off, off. Come on. Fail off. Come on, off, 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 off. I think we're jumping ahead some pages, Simon. I think we need to go back to 257 we were at. 260, 259, 256. So failed off, off in flight. Was it the word resolution? Come on, Si, what was it? Resolution. It wasn't resolution. What was it? Come on, what was it? 250. Potential resolutions. Resolution. No, it's not that. Ah, what was it? What I'm trying to remember is maybe I'm reading between the lines where there's nothing to be read. Maybe I'm misunderstanding something, but I could have sworn somewhere earlier on at the bottom of the page we were talking about the assumption that they'd made in the way they measure things, and that it was just on or off. Let me just. I'll be quiet for a minute while I find it. Just bear with me. If you want to get a fresh drink, you can while I just find this. Right, so thruster heating, qualification levels, mission phases, in-flight locations, limited in number, data rates, primary design challenge. It's Quest. I think it was after this, Simon. Hard failures. Telemetry. Seat swelling, NTO bubble formation, thruster chamber pressure sensor sample rate. Soak back, propulsion system temperatures. Mature. Turnaround between tests. SM fire. Thermal sensors. Noted high temperatures. Not validated. Not well integrated. I could have sworn I read something about the resolution of the sensory feedback, and it was assumed. Maybe I'm missing. It's not about. Yeah. Hmm. Yeah, I don't know. I'm going to have to search for that. I think I might be misremembering something. But anyway, right, okay, let's keep going. So increase the data rate of chamber pressure measurements on the Starliner 1 RCS thrusters. Lessons learned. NASA has insight to critical component design details, even if that hardware is produced at sub-tier suppliers. That sort of breaks the intention of the new shared assurance model, though, doesn't it? Is that really what we intend to do? Is that really necessary for safety? I'd argue it probably is, because they've got the experts, and maybe Boeing doesn't have the experts, and they need that expert review and build that trust again. But I don't know. I think it'll help in the short term, but it might make things more complicated in the longer term. Integrated testing of the propulsion system in a flight-like configuration is an essential element of system verification and validation. Absolutely agree with that. Validation of induced environments through ground and flight testing is also essential, yeah. Invest in ground testing to requalify propulsion system hardware, particularly when updated trajectory, design maturity, flight experience or in-flight anomalies show that anticipated usage and induced environments are exceeding pre-flight projections. Yeah, I mean, again, that should go without saying. So, yeah. Tear down and inspect ground test hardware to ensure the impacts upon soft goods are understood for both commodity exposure and combined environments testing. Fantastic. Okay, so that is the OMAC thruster. All right, here we go. So let's just check this with this one. Let's just make that bigger. Let's just check it, make sure it looks like it makes sense. So it's pretty much everything except that grey one. Yeah, okay. Okay, right then, let's have a look. So the next thing we're going to look at is the SDRT report. So I'll just put a big black, in fact, I'll use a brighter colour. Let's use, blue. It's not really going to work, is it? Let's use this blue. There we go. So this is the next section. So if I just jump to here. So we've just done the thruster bit, and now we're going to go into the SDRT report. So this is like the second report embedded within this report. And I think what we should do is maybe just have a quick 5-minute break. And then we'll, in fact, actually, I think we should have a break there because it's quite a few. Right. Okay. Yeah. So this section is quite long. So it's 3, 6, 9, 12, 13 pages. And then once we've done that, the senior review panel, Star Senior Review Panel, that's basically blankety blank all the way through. So let's mark that off because we can't do it because there's nothing in there. Let's put that down here at the bottom. Mark it off. There we go. And then let's just have a look back at this. So the Star Senior Review Panel summary. Hang on a second. So there is a bit we can review on that actually. It's not completely lost. And then, and then we're into the appendices. Okay, so I think looking at the clock, it's 8:15. I think what we'll do is we'll pull stumps there, and then I'll call another live stream ASAP in the next couple of days, I think. And we'll finish off this report. And I think within an hour, 2 hours, maybe 3 at most, an extended session, we'll have nailed it completely. And so, so let's just jump back to here. So where's the button? There we go. If you want to take part in the free workshop once I've finished these live streams, please visit my website, click the link in the chat, join the waiting list, and when I'm ready, I'll send you a message. We can get on a Zoom call together as a group, live with cameras and audio, and we can talk to each other about Stamp STPA Cast in this context. And of course, if you've got any questions about Stamp STPA or Cast in your own context and you're happy to hear the answer in a public forum, then you can bring those along. And if you would like to talk to me personally, please visit my website, press the green button, I need help now, send me a message, we can set up a call and answer your questions privately. So yeah, fantastic. Thank you very much for your attention on the 30th live stream. I'll see you on the 31st very, very soon. Take care. Have a good night.